Welcome to the Intersecting Us podcast, where math and life intersect.
In today's episode, Brian and Dave take a look at math's evolution, from concrete concepts to abstract abstractions. Brian and Dave discuss redefining math, unveiling numbers and operations.
Today on the podcast, we're going to continue on trying to look at math and life and maybe the different perspectives like we have through all of our Intersecting Us podcasts. The different ways of maybe rethinking math. I know, Dave, you're trying to do that in a number of different ways, but maybe today you could start off and tell us a little bit about a special way of rethinking math that has to do with action.
Well, great. It's always good to be here, Brian, and hello to everybody. And, I'm always kind of on this journey of trying to figure out what makes me so excited about math. And I think I just love the idea of discovery is one of the things I like. I like to see things from different perspectives. I like to connect dots. I like surprises. And I like to see complicated things kind of like turn into something like really simple. And then, of course, sometimes really simple things turn into complicated things. Maybe that's part of the surprises. But there's always a puzzle to be had. And one puzzle just not only leads to another, but kind of like fits another one. And when we think about the numbers, that's a great example of the interconnectivity of math, of numbers and operations. And so I want to help us to rethink what it means to do basic things like addition, subtraction, multiplication, stuff like that, and why we even need numbers to begin with. And things we take for granted, but so often maybe don't really think too deeply about why we have things the way we have them. And today we're going to revisit why do we have numbers and why do we have these operations?
Yeah, and I think one of the main things that we all learn basic math probably when we're in elementary school, even you always try to conceptualize numbers so you could understand how they work. And one of those is that number line. So when you do a number line, it helps us with things like addition, subtraction, multiplication, which I guess probably most people listening know what that is. But I know even when you get into higher math, there's questions about what exactly is that. I thought maybe you could talk a little bit about that, maybe from a different standpoint, maybe a little more fun standpoint of what is addition, subtraction, multiplication.
Well, sure. You brought up a point that connected something I recently read. And it talked about the levels of abstraction of math. And it talked about like numbers, but numbers were like at the level 2 level. And there's a level below that. And those are things like if you see dots on a domino, if it tells you, okay, if you've got 5 on a domino, you'll see 5 dots. And so that is something that we can count 1, 2, 3, 4, 5. So that is like level 1. And then the idea of a number where we assign concept to that count. So 5 dots is the same as 5 animals that both are 5, and we just write the number 5. That's a level 2 abstraction where we kind of think of numbers as level 1, but really numbers are just abstracting things that are for the number 5, things that have 5 in them, and we just collectively call that 5. And, there's levels above that I'm not going to get into today, but I hadn't thought about that before because we do all this stuff very naturally as we do math day to day, and we kind of forget all these different levels of abstraction that are out there. And so even numbers themselves are, a pretty big abstraction from counting.
So we're at least doing level 2 math now, which is nice.
That's right. Yeah, we're not at level 1. We've already skipped level 1. Now we're up to level 2. So yeah, that's a good way of thinking about it. So a number line, again, we take that for granted. You may think about a ruler. That's a number line that we're familiar with, and it's broken up into parts. It took a long time before number lines were really a thing in the math world. And so again, it was something that had to be invented. And when we did it, then all of a sudden, a lot of cool things happened. But let's just start from the basic. You start at 0. 0 took a long time for that number to be invented, but eventually we got 0. And then, you can go up to positive numbers 1, 2, 3, 4. And the first thing we probably want to do is add those guys together. So 1 plus 2 equals 3, 3 plus 1 equals 4. If we think about all the positive numbers and we think about addition, that covers everything. We've got a complete set. A closed set is really what you want to think about. In other words, if I have a positive integer and I take addition to another positive integer, it's going to result in another positive integer. So it is complete and it's closed. And so there's no need to introduce anything else because everything works just great. And if all we did in life was add, we probably would be stuck with the positive integers, because what else do we need to do if we don't need to just add positive numbers? But then, there's that word of subtraction that happens in life. And so subtraction probably has meaning for you, Brian. Is that right at all?
Well, it does. As you were saying that, I was trying to think if there was anything in life, that you use the numbers for that you wouldn't use subtraction much. And I do think, time, because we're talking about eternity to some extent, and I'm just kind of thinking out loud now, your time goes forward. You can look backward, but you can't really go backward. I mean, no matter how hard you try, at least as far as we know right now, you can't travel back in time. But I do think, subtraction comes up pretty quick in all other ways you use numbers. But when it comes to time, I guess we're always kind of going forward. But on the number line, of course, you're going to have go back and forth in subtraction. If you're going to go to the left, you gotta have subtraction. Addition's not going to do it for you.
Right. And so we can take 5 minus 3 with the positive integers and land on 2. So that's no problem. But if we reverse it and try to subtract 5 from 3, then we have a problem because the result is not a positive integer. And so our nice system that we had that was clean and pristine, positive integers, life was simple, life was great, all of a sudden hit a roadblock. But mathematicians, when they hit a roadblock, they don't panic. They say, we will just invent our way out of this problem. We'll define our way out of it. And so we will now define negative numbers. They didn't exist yesterday, but today they do. And so now negative numbers exist and that problem is solved. And now we have subtraction and we can take 3 minus 5 and there's that minus 2 number and it's there. And now addition and subtraction are closed under the positive and negative integers.
So you're still staying on your one-dimensional, well, two-dimensional, each direction number line.
Yeah.
But it's really more of a different direction. You're going to the left instead of the right.
Yeah. And so everything works nice. There's symmetry. If you think about a number line, now instead of going right, we're going left. The units are the same. If 1 was like 1 square to the right, we go 1 square to the left. And so there's not like a whole lot of invention that needs to be done or really a lot of imagination, but there still was a lot of I's to dot and T's to cross in order to make sure that all of the rules of addition still worked with negative numbers because math people like consistency. They don't want to start over and say, okay, we're going to go to negative numbers and we're going to start from scratch. That is a bad strategy in math. In a sense, they're kind of lazy in that, okay, we've already got things figured out with addition and positive numbers. Let's just kind of not reinvent the wheel and try to make sure everything's consistent. So it takes work, but once it's done, there's very little learning curve to bring in the negative numbers.
Well, I think when you look at the concept of it, we're thinking about the math world. We've been talking about that in a lot of our podcasts and videos about how the math world is its own kind of world, which is kind of cool that you can do things that you can't do in the real world, especially when you get into multiple, you get to the 5th, 6th, 7th dimension in math. It's not that hard. You just use new variables. But I could see, and I remember reading about this, negative numbers were something that people, I don't know if there was like a anti-negative number group or whatever, but it was abstract for them. I mean, you can't take 7 apples away from 5. I mean, in real life, if that, because that's the way we usually do it in math. Johnny has 3 apples and you take 2. How many apples do you have? But if Johnny has 5 apples and you take away 7, you look at Johnny and you can't do it. You can't do that particular concrete thing. But that's really easy on a number line. Right. And I think, again, it seems so simple on one hand. But if I remember reading, I don't know how long ago this was, but you talked about 0, something that we really didn't conceive as a number till actually fairly recently in human time anyway. But, you kind of go against that. You're like, well, that doesn't make any sense. When are you ever going to get a negative number? What am I going to have less apples than I've ever had?
Right.
Either I got 0 or I got some. It's a very easy way, I think, for people, even if you're not a math geek, to realize that you pretty quick get out of the concrete into more just the math world, but yet then you find out how wonderful you can do things. And then it works its way back into the real world. And we see that with some of the Eulers and the Einsteins that use these numbers and come out with real formulas that work in real physics.
Right.
Here, Brian and Dave attempt to unveil the mysteries of mathematical creation and discovery.
And there's always this debate in math about what is discovered and what is invented. The difference is discovered means that something was already there, and we just happened to run across it. And then invented meant that it really wasn't there, and it was something that was brought into life. And when you're talking about things that are abstract, it's kind of difficult because it's abstract. You could argue either way, as opposed to back to your apple, either I produced the apple out of nothing or I didn't. And so it's kind of concrete. So the debate in mathematicians over the beginning of time has been, what is discovered and what is invented. One famous mathematician, his name was Leopold Kronecker. I'm not quite sure I'm pronouncing that right, but he was in the late 1800s, and he said that God made the integers, all else is the work of man. And I remember reading that maybe 3 or 4 years ago, thinking about, well, that's just kind of a nice saying that I'm not quite sure how important that is, but I've stumbled across that in many different books that I've read. It is frequently quoted, and it is kind of this perspective that we were given the integers, and then we invented the other numbers after the integers. And of course, there's probably not a right answer, and this is above my level of understanding, but it is something that is not trivial at all. And it really is interesting to think about, because when you start seeing patterns occur, you start asking the questions like, where did they come from? Why do these patterns exist? And then it eventually leads to like, where do the numbers come from? Why do the numbers exist? So anyway, we're only on the positive numbers, and I guess we got to keep going here. We're only on the integers, and we've done addition and subtraction. And if that's all we did, life would be great. But we know that eventually we don't just get a whole pizza, we get a part of a pizza. And so when we get a part of something, we can't calculate what that part is with just integers, other than we can say it's a part to a whole. But if we want to say, well, 1/2 or 0.5, that is not an integer. The 1 is an integer, the 2 is an integer, and that makes it a rational number. But the value itself of 0.5 is not an integer. And we all know that there's the idea of halves and wholes. So we had to come up with math to manage this idea. And that introduced a whole nother challenge for math people to think about.
Well, and then you come into the fourth one on all our, even our little itty bitty calculators that only have 4 functions on it. You've got addition, subtraction, multiplication, and now we've got division.
Right.
The idea of dividing something, like you said, dividing a whole pizza into 8 pieces, or if you're really hungry, you can divide it into 12, right? Is that how math people get that? Maybe. I don't know if everybody does, but I think
I was wondering, it's like, that doesn't make sense, but now I get it. It was a joke.
Now you get it. It's like, if you're really hungry, we'll cut it into more pieces for you. You know? But I, when you were talking about that, you know, one of the things obviously I like to talk about is the philosophy. And I don't know if people even know this, and we don't have to get into it, but just as a discipline out there, there is a philosophy of mathematics, you know, which is, the study of, the assumptions and foundations and parts of math. And I know you were talking about whether something is in math, and this is true in lots of things, but in math, is it discovered or created or, discovered or invented, however you want to put that. You know, I remember Plato dealt with that a lot, not with just necessarily numbers, but with ideal forms. You know, did we discover the ideal form or was it created? You know, I think the one he usually uses like a chair. Is the form of a chair, is that somewhere out there in perfect Godland or whatever, and then we discover it? Or is that something that we create because of our minds being able to be creative? And then so you go to the numbers. I remember reading, this has been years ago, about, there's still some people who are what they call anti-realists when it comes to numbers, and some people who are realists when it comes to numbers. And this isn't talking about really real numbers. It's talking about whether or not numbers really exist or they're just our invention, creation to name something.
Right.
Or to point to something.
Uh-huh.
I don't know if you have a position on that. You don't necessarily have to have one. I think you would if you're going to write a dissertation in the philosophy of math. But I think back to what we're talking about, this is more the idea of a lot of these things you're talking about. We're talking about such simple things that we all learn in, I don't know what grade it is, first, second grade, math, addition, subtraction, multiplication, division. But we're all getting into this. Are these real? Is this something that is real in itself, or is it just something we've invented so we could use it?
Mm-hmm.
I don't know if you have anything more to say, but I know you want to talk about kind of multiplication and division, how we can look at that.
What I like is just the logic of it all, that underlying everything, math desires to be complete. So a complete system. And so addition and the positive numbers is totally complete. And that system works until we decide to bring subtraction into the game. And so we are introducing an idea of something we want to do, and then coming to the realization of what we have isn't enough. And that is something that happens all the time in math. And we usually don't understand that very well, because in our day, there's been so much that's been discovered. It's been perfectly prepared for you. It's kind of like when I show up for a Thanksgiving dinner. I usually don't do too much for food preparation. I hate to admit. I show up.
How it gets there. It's amazing. It just shows up.
I just show up there and it's there, but that is very naive to think it just happened. And there was a lot of planning. There was a lot of thought that went into it. And I'm not saying that we don't realize there was not a lot of thought in math, but it was a process of having something that works and then wanting to do something else, and it doesn't. And then there's this thought process of, we want this to work. We think that this is something we want in math, so let's work our way through this and invent something to make it happen. And so when we're talking about this with the numbers, it's working with very common things that literally took centuries and millennia to put together. And we take it for granted how simple and easy it is. But I imagine if we happen to think about what it was like when we were like in first grade, some of the stuff was a bit of a challenge to teach and understand. But we've also been able to be put in a position where it's been packaged in the nicest, cleanest way that we've learned over time. And so we've taken out a lot of the struggle that was present over hundreds of years. But it's just kind of neat to think about how this all came together. And
yeah, the thought processes you're talking about, there's so much similarities between, I was thinking about like Edison or whoever. When you have an invention, you're inventing something that doesn't exist yet to do a particular task that you can't do unless you have it. You know, and that is really not a different thought process than coming up with the number 0 or figuring out negative numbers or looking into, you know, rational numbers because you need to divide the pizza. I notice I know in some of your math stories on our website, Lazarus Math and others, some of the videos, it's almost like, you know, and what are we doing in this podcast? We're always trying to get you to think not necessarily differently, but maybe better or deeper, because the same thought processes you're using just to show us how addition, subtraction, multiplication, division, negative numbers come into things.
In the next section, Brian and Dave discuss different perspectives, seeing math as action and logic.
Is the same thought process some of the greatest inventors, that it's that same idea. It's the maths behind all this stuff, whether it's science or physics, or it's the same way that this does not work in the closed system I have. So I've got to figure out a way to open the system or change the system to get this to work because we need it.
Yeah, that is really, I think, hits the nail on the head. And there's been so many times when I have been struggling with an idea in math, and I'll just give it a name, and then I find out that someone else actually has a formal name for it. And it just happened to me this last weekend. I was working with Pythagorean triples, and I just happened to think about this, but I was trying to work with a wide variety of Pythagorean triples, and they're numbers that are like 3, 4, 5 that work in a right triangle where they are integer values. And there's all kinds of cases out there, but it's easy. If you got 3, 4, 5, you can get another one by multiplying it by 2. And so then you have 6, 8, 10, and then you multiply by 3. You have 9, 12, 15. But anyway, the idea was I came up with this idea that, okay, I needed to find the root one. And so I just labeled it the root one because I saw it as a thing that was important. But I never read it in the book. I'm just kind of learning a lot of this stuff on my own. But I realized, okay, I wanted to define something here because this has a functionality in math. And then about 2 hours later, I got out this big, thick textbook, and I found out that in this textbook, they defined the very thing I was thinking about. Now, they didn't call it the root case. They called it the primitive case. But there was something really cool about me realizing, okay, I want to define this thing because it's going to be a pattern that's going to be repeating over and over again. And it's like a special case, and I can recognize that. So I'm just going to give it a name so that it makes sense to me, so I can refer to it, and then to see that, the math geniuses around already realized that it needed a name, and they just gave it primitive. And so, I don't know, that was just special to do that. And I don't think a lot of people feel like they've got the freedom to define things and create their own math as they see fit. And as they run across things that they need, it's like, okay, just define it and take that definition and move forward. Those things are very powerful in math, and it's the foundation of how math is built, and it's available to all of us. We can define things however we want. Now, once we define things and set things in motion, then logic dictates what we can do with it. But we're free to define anything we want. And that is a pretty cool thing to have that much power to create something that never existed before.
Well, it is a little bit like somewhat, it's not exactly the same, but like the scientific method, you hypothesize something and then it doesn't work and then you change your hypothesis. But in math, it's almost, it's better because you don't have really any physical things you have to worry about. You can come up with your own. We talked about that, I think, in a past podcast. The Euclidean geometry didn't work right when Einstein was working, but he found one that worked better, that dealt with parallel lines a little bit different. And then all of a sudden the system changed, but he didn't have to use any type of heavy metals or anything. It was just all in his mind and in the concept of just changing math to work in a different way. And that's, he was one that was innovative. There's been a lot that have done that. And so I think you can make a case anyway that it's almost better to do it in the math world than the physical world, because it's just pretty much unlimited on what you have, the possibilities that are there.
Right.
Like eternal, we could say.
And we actually do that without knowing it, just by simply identifying what letter to assign a variable. More often that will assign X as a variable, like an unknown, right, if we're given a stored problem. That's inventing something that was not there. You're the one that wrote X as a label, and you're the one that defined what X represented. And that was something you have the power to do. And I know it's hard when people just do algebra, because all of a sudden they don't have rules to follow. Like, what am I supposed to do here? And it's like, okay, you're supposed to use logic, and you're going to have to use your brain in a way it's never been used before, because there's not like set rules you can always solve problems for. You're going to have to follow principles and not procedures to get through algebra. But,
I think you've got those different ways of trying to look at the same thing. And, the way you may teach math and all those things. And I know you've even talked about like multiplication. You can look at that in a different way. You don't have to look at it just with the rote multiplication table memorization. And maybe you could talk a little bit about that.
Well, when we learn multiplication, because now we've got positive and negative numbers in there, it always makes sense that 5 times 5 is 25. That was there in the beginning before negative numbers came about. So we certainly don't want to change that. And then we go 5 times negative 5 equals a negative 25. Or we can reverse it. Negative 5 times a positive 5 also equals a negative 5. So if one of them is a negative, another's a positive, then that results in a negative number. I think most of us learn those things, at least I probably did, by a rule. It's like, okay, if you have 2 positive, it makes a positive. If you have positive and negative, it makes a negative. And it's not like too difficult as a rule. So we eventually get it, but it's not like we're sitting there thinking, oh boy, that just makes a lot of sense. It's like, no, nobody's asking you to make this sense. That it just needs to be something that you remember. But
you remember the rule.
You remember the rule.
But you don't really know why, because the ultimate one I think of is why, and maybe we could kind of end up with this. Why would something like, and you had a negative and a positive, but why would something like -1 times -1 equal positive 1?
Right. That even is a bigger stretch, because it doesn't make sense in a lot of common sense areas. But if we think of multiplication as an action, as a rotation on the number line, and so if we start out with a positive 5, and then if we multiply something by a negative 5, then we reverse directions from where we were at, and we do a half turn and then go to the negative side. And so we had a positive 5, we multiplied it by a negative 5, so we went the opposite direction, and that left with negative 25. And then if we started with a negative 5, now we're going negative, and we multiply that times 5, or positive 5, we keep going in that same direction, and we still land on negative 25. Okay. So the idea is a positive means keep going in that same direction. A negative means you rotate a half a turn. Now, that's something simple to think about. We can all imagine literally walking on a number line and following that rule, and to see if that makes sense. So then if you add the idea of a -5 times a -5, well, then you start out with a negative 5 going in the minus direction, multiplied it by another negative 5. The magnitude is 25, but we have to reverse direction. We have to take a half of a turn, because we're following this principle that if we multiply by a negative number, it means we perform a half a turn rotation. And that's going to allow us to land on a positive 25. Or in your case, if we're doing ones, we would start at -1, then multiply it times another -1. And that's going to reverse course and land on a positive 1. And so if we think of multiplication as an action of either rotating or not rotating, then once we have that idea in place, then we don't have to remember anything else. There's not like 3 or 4 different rules. We just have that one definition of how we think of multiplication. And the cool thing is that's something we can think about physically, and it's not even abstract, because we can imagine walking on a number line and simply rotating half a turn if it's negative, and if it's positive, we just keep going in that same direction.
And it makes sense as you were saying that. I was thinking about doing a ship where you're going east and you turn around and go west, so that it starts to make sense, where something, like you said, when kids are learning math or adults or whatever, you have these rules. Well, I just follow the rules, and that can work if you can remember them. The rules still work, but you can still remember them. But now you know why they work, because you're changing direction, which makes more sense than just switching the sign or whatever.
Right.
You might, yeah,
very abstract.
Yeah. So,
the nice thing is that scales as you get up in more math. There's just all kinds of things that build on this idea. And if we don't start with this idea of action as multiplication as the act of rotating, then when we build on more advanced math, we're just going to have to learn more rules. But if we think about the basics this way, when we get into more advanced math, we simply kind of extend the story a little bit, and it seems extremely logical because we're already thinking in terms of multiplication means rotating. And so you've already got that seed planted in your mind. And it was really cool. And we're not going to get into where that goes today, but that will be a future podcast.
Yeah. And I think this is good. This was good. Again, it was such rudimentary things, but you'd start talking about it and thinking about it different. And that's kind of what we're trying to do for ourselves, certainly, but even for you guys is, how you think is sometimes almost as important as what you're thinking. And if you think of things a different way, different perspective, you come up with some pretty cool things. And it isn't so much about memory. It becomes more just a part of who you are because you just know how it works. So hope you enjoyed the podcast. We'll hope to continue to have you tune in, subscribe if you haven't done that so far. We'd like to have feedback from you too. You can click on Intersecting Us there. Go to YouTube channel 2 if you look at one of our videos and give us some feedback here on Intersecting Us.
This has been the Intersecting Us podcast. To further engage with Intersecting Us, go to intersectingus.com.